So my name is Christian Bueno. I'm from Florida International University, and the title of my presentation is The Representations of String Links and Tangles. Before we can get to the heart of the project, though, we have to do a little background and understand string links and braids first. So imagine that you have a set of points, a set of sources, and a set of ending points, equal number, and that you have strands flowing from the starting points to the ending points. They may intertwine or interlock, however, but if we add the restriction that these strands may not turn back and go back down, then we'll have braids. Notice how these do not ever go back down. They only flow from bottom to top. If we remove that restriction, then we're allowing looping things like this, and we call those string links. There's also this notion of equivalence between string links, that if you can deform one into the other, they're the same. For this one, if you just tighten this one up and tighten that one up, it will be identical. So these two are equivalent in our notion of equivalence. There's also a notion of multiplication, which is shown here, that if we take this string link and this string link, and we define multiplication by the stacking, we put this one underneath there, and we get this. And you can kind of convince yourself that that is what happens. This turns like that turns like that, the loop is still there, and everything is like that. So that is string link multiplication. With this operation, the braids form what's called in math a group. It's a kind of algebraic structure, and the string links form what's called a monoid. And the groups are nicer than monoids generally. And in particular, this one is finitely generated, so it's even better than some groups in general, because all we need is a finite number of braids to be able to, through multiplication, get every other braid. This is not true for the string links. You can never have finitely many string links that through multiplication will give you all the string links. In the study of abstract algebra, representation theory is oftentimes employed because it simplifies the study of these objects, which are generally very abstract and complex. And the way it does this is representations are these functions that take elements of your algebraic structure and turn them into matrices in a systematic way that also preserves the algebraic structure, in the sense that if you have A times B equals C in the original algebraic structure, the matrix of A times the matrix of B will equal the matrix of C in the transformed algebraic structure, in the matrix structure. And so it carries the multiplication in some sense. We're going to be needing these because the next three things are going to be the Borel representation, the Lin representation, and the Skane representation. The Borel representation is the first representations for braids historically, and it was defined by this guy named Borel. And he defined it by defining it over the generators of the braid group, because it has finitely many generators, and in a way that satisfies the braid relations. And once he did that, he's done, systematically defined the representation for all the braids. The next representation we're going to discuss is Lin's representation, which is relatively recent. And it applies to string links. It is, in a sense, in an actual precise sense, a generalization of the Borel representation, because Lin's representation equals the Borel representation whenever you plug in a braid. But for string links, it's a whole new thing. And the way he defines it is by this idea of a random walk along string links, that if you start at a strand, you pick a strand, and then you traverse the strand, travel along it. And whenever you get to overstrand, you may fall off or you may continue with a certain likelihood, quote unquote likelihood, because they're not always, it's not good to consider them as probabilities always. And so doing this and figuring out the likelihoods of starting at the first strand and ending at the second strand, perhaps, you can start building all these likelihoods of going from the ith thing to the jth thing. And we use these probabilities, quote unquote again, to build the matrix that corresponds to the string link. And this table summarizes pretty quickly what the probabilities are. There's two types of crossings that we consider. Well, there's two types of crossings, period. Positive crossings and negative crossings. For a positive crossing, you can fall with probability 1 minus t and continue with probability t. For negative crossings, you can fall with 1 minus t inverse and continue with t inverse. And this is actually the reason why it can't be considered probability, because you have these inverses. Yes. And so if we compute the matrix for this string link, we get this matrix. And I excluded the computations because it's complicated computations. But the other interesting thing about Lin's representation is it doesn't depend on the choice of diagrams, that if I were to compute Lin's representation for this and compute Lin's representation for this, taking into account all the overcrossings and undercrossings, I would get the same answer. So it doesn't depend on the choice of diagrams. So that's Lin's representation, and here's the example. So the skein representation is the second representation that pops up in our project. And it's defined by using the famous Conway-Skein relation of knot theory. And what that relation does is it says, let's zoom in on one crossing. And if it's a positive crossing like this one, we're going to say it equals the same string length times z, but with that crossing now changed so that it's smooth, plus the original string length with the crossing reversed, so that it's a negative crossing. And that is the Conway-Skein relation. And if we successively apply this, we successively reduce the complexity of the string length. Eventually, we boil it down to braids. And after that point, we apply two new representations that we're going to need to define the skein representation. The first one is called the scaled Borel representation. And it basically is the Borel representation with a scaling constant for every generator. And the scalar representation, which is a representation that just sends all the generators to some power of t. And so you get a polynomial in the end when you distribute over all the braids that you end up after dissolving the string length. So the first step is dissolve. Boil down your string length to braids, to sums of braids. Then apply the scaled Borel representation, get your matrix. Apply the scalar representation, get your polynomial. And then divide the scaled Borel by the scalar. So in this example, we take this string length, same as before, look at that crossing, smooth it out, times z, plus the crossing with the reversed crossing. It can be simplified to this and that. And then apply the scaled Borel, get this matrix. Apply the scalar representation, and get 2 minus t. And when you divide, you get this. So that is the skein representation of this string length. And if you notice, that's the magic. Those are the same matrices. It's the same answer. And so that's a bit mysterious. It's understood that these are two representations of, two extensions of the Borel representation. So they agree for all braids. Skein and Lin will give the same answer for braids. But for string lengths, it's a bit of a surprise that they give the same answer. And this begs the question, will there be other string lengths for which it agrees? And our research was to find more evidence for this, or to find counterexamples, or to even prove it. We did find more counterexamples, more evidence. And here is 2 examples. This is a string length on 3 strands for which Skein and Lin agree. And this is technically not a string length, it's a tangle. And it also agrees here. We found a way of extending Lin so that it can also encompass things like this. Furthermore, there's this infinite family of string lengths for which Skein and Lin agree. And the nice thing about this twisty family is that it's not finitely generated, kind of like the string lengths, which there's no way to encapsulate all of them with finitely many string lengths. You can never find finitely many string lengths that through multiplication give you every single one of these twisty string lengths. So in this infinite family, whenever you apply Skein and Lin, will always give you the same answer for a particular one. This is good. And there are more examples, but this is another huge family of examples, this theorem that I proved. And it basically says that if you have a string length with n strands, and all the strands can be separated, basically, like the strands don't interweave. They're just, you can group them by themselves. The strands are independent in a sense. Then that n-stranded string length will always be sent to the identity matrix by both Lin and Skein. They'll both go to the same place. And that therefore means they agree, of course. You can even extend this a little bit to this tangle-like stuff with loops, so long as the loops doesn't lock on to 2 strands and just one at a time. Same will hold. They'll be independent, and you'll get identity matrix. So that, again, a huge family, not finitely generated set of string lengths for which Skein and Lin agree. Lastly, after not being able to prove that the conjecture is true, just finding a lot of evidence, I kind of jumped ahead and said, what if it was true? What would follow if it was true? And a consequence popped out saying that the famous Alexander polynomial, which is related to the Skein relation, that the Alexander polynomial of a knot that comes from a string length can be expressed in terms of the scaled Borel representation. Only one term of the scaled Borel representation times a constant. And so this is neat. It may be new, it may not. We'd have to check, but it's a consequence, something that follows from assuming that the conjecture of Skein and Lin being equal in all cases is true. Future work can be done in finding more consequences, or hopefully even proving the entire conjecture in its entirety. But that's all there is for now. So I'd like to thank Ohio Wesleyan University for hosting me, the NSF for paying for everything, and my mentor, who was great and very patient and good teacher. So thank you.